Thank you for waiting. We would like to begin part 2. In the second part, we will have panel discussion and Q&A session. We have the 3 speakers who made presentations. We will talk about user needs and LSI directions. We will have panel discussion on this topic. So let me introduce our facilitator and panelist. Facilitator is the BU President MR&D of Sharp Corporation, Mr. Taneya Mototaka. Let me introduce our panel. Dr. Shang-Yi Chiang, Foxconn Semiconductor Strategy Officer. We also have Professor Katsuaki Suganuma of Osaka University. And from METI, we have Kanazashi Hisashi, Director of Information Industry Division, Commerce and Information Policy Bureau. And we have 3 panelists from Sharp. First, Deputy General Manager of Society Innovation Laboratories, Dr. Norio Ito. And Division Manager of Process Development Division, Panel Semicon Laboratories, Mr. Naoki Makita. Also, we have Mr. Toyofumi Horikawa, Division Manager of Development Division 2 of Sharp Semiconductor Innovation Corporation. So without further ado, I'd like to now ask Managing Director Taneya to proceed. Thank you for participating in the first part. Now we will start the second part for discussion to talk about near future, how it's going to change our livelihood, how LSI is going to take part in that change. We talked about how Moore's law is coming close to physical limits of 2 nanometer. This has been discussed by Dr. Chiang, as you can see on this slide. On the other hand, we're now looking at AI, generative AI. Since the end of last year, this has been a hot topic. It has already impacted our lives and businesses. I'm pretty sure many of you are already users of generative AI. Naturally, this is evolving based on LSI and semiconductor technologies. As Professor Suganuma and Dr. Chiang said, we need to go beyond Moore's law to generate values. So that is the challenge, the breakthrough that we need for our technology. Today, we're not going to particularly talk about AI, but as AI is going to be part of our lives, for LSI to be able to evolve, what technologies do we need? Including 3 engineers, technicians from Sharp, we are going to have panel discussion. The 3 guest speakers who already made presentations, I would like to now invite the 3 Sharp representatives to introduce themselves and discuss what technology they're engaged in, what technology they're developing, and then perhaps share with us the near future they would like to see based on the technologies they are developing. So first, I'd like to invite Dr. Ito to talk about the near future based on AI. I'm Ito from Sharp. As was just discussed, I have focused on image compression and standardization. So I have always been the user of LSI. But for the past 4 or 5 years, I have been involved with AI, considering what AI is going to bring in the future. So I'd like to share with you my thought on future AI. For the past few years, I have been working on this specific issue, where AI is going to be used. The first thing we worked on is image compression. This has been developed over 20 years, but in many different ways, it has come to limit. So we want to overcome that limit utilizing AI. We're looking at converting 4K to 8K resolution, the super resolution. Thus, we may be able to improve compression ratio. In terms of algorithm, we'll be able to achieve double the performance. We expect the performance may double as a result. So if we implement this on the hardware, as you can see, the left-hand side, since this is AI, we are going to use GPU. The image codec is placed on the edge. So GPU cannot consume a lot of power. In this world, we cannot afford to consume a lot of power. And conventional AI chips, we have low power consumption. So that's the conventional device. But for image compression, we have to go beyond that. We have to process many per a unit of time, and we have to be real time. So rather than general purpose, we are focusing on super resolution for our development. Compared to ordinary GPU, FPGA will achieve 47 times efficiency. Maybe with hardware ASIC, we can go beyond 650 times. On the other hand, in this low power consumption world, for us to be able to improve performance, of course, it's a major challenge. So we have to review our algorithm. So please look at the right-hand side. We have super resolution technology. And those circles, we have different technologies. The size of a circle indicates the degree of complexity. So if you apply complex processing, you get a better image result. So vertically, we have the quality, and horizontally, we have processing time. So with complex algorithm, as you can see, the circles are drawn on a higher right-hand side. So we need to achieve high performance and good image quality. So achieving both, we need to have real-time coding. So one thing that I need to focus is the real-time. It has to be real-time. So how is AI going to be used? I'd like to use an analogy to human brain. We have cerebrum, which is a rational brain, and we also have limbic system, which is more intuitive part of a brain. And both of these are organically combined together when we make a decision. If you need to avoid danger, you need speed. The limbic system is in charge. Likewise, in the AI world, the cloud is a processor. Cloud is processing. Edge is also processing. There are two processors, and they have different purposes. Especially on the edge, this is similar to limbic system of human brain. It is going to make life or death decisions. So the requirement there will be the real-time response, and processing capacity or power consumption are going to be limited. And in this world, if you're going to process image or moving picture or video, so that will be the context. And recently, we talked about ChatGPT. This is an example of large language model. So it is about generative AI. 175 billion parameters is the size of this ChatGPT, so big. Having said that, you cannot make it larger easily. You need to feed a lot of data, resources of calculation. AI will become smarter and smarter. We know that. Having said that, in order for us to utilize many GPUs, it consumes a lot of power. You have to pay for that electricity. So from the economic point of view, it's very difficult to make it larger than what it is today. Though there is also a specific language model dedicated to, say, a Japanese language or Chinese language model. So that is a recent emergence of AI models. So the size of the parameters can be reduced from 175 billion to 1/10. What is important is for each model, the fact is that they are not interacting with each other. They are not connected with each other. Compare that to human brain. We want AI to become smarter and smarter, but considering economics, it cannot be as large as we want. So that's the current situation that we are faced with. In 3 years or 5 years from today, what will happen? So the focus is on the right-hand side. So AI, we believe there will be multiple AI models. So ChatGPT is there, and other than that, there may be legal AI, educational AI, or medical AI. So separate, dedicated AIs, they will play different models, and they will be interacting each other. And they will be placed on the cloud. What about human beings? Closer to humans, there will be a different type of AI. So for now, I'll call this personal AI. AI is close to humans, so interaction is faster, response is much faster. The training data, people worry about how this can be leaked. But since you have a local AI, you can contain data within that local AI, so you will feel safe about data privacy. So that will be the future of AI, and the personal AI will be there to provide support for human beings. So the key here is speed, quick response, and make the response easy to understand for the user. That will be the key requirements in this world. Thank you.
ありがとうございました。後ほどこの AI と
Thank you very much, Dr. Ito. So regarding the AI and implementation technology and how it evolves and so on, we will deep dive such topics. The next speaker is Mr. Horikawa. Dr. Ito talked about AI. But going forward, our AI world, to realize that we have to have a wireless communications. This is an indispensable part. It's a basic technology, and LSI is playing a large role in this. So going forward, even further customization and flexibility will be needed. So now initiatives and efforts are underway. So Mr. Horikawa will talk about them. And then he will also talk about his ambitions and dreams of what sort of AI world he wants to realize. I am Horikawa of SSIC. So let me first introduce myself. So in April 1993, I joined Sharp. And for about 10 years, I was engaged in the development of a mobile terminal, ZAOS. As you can see at the left bottom, this is a very old thing, so many of you may not know about this, but I was engaged in this development, fortunately, and mainly cameras, music, playing a function, and so on were my areas, and I was engaged in the development work for as long as 10 years. But then I thought, wait, so to develop new things, key devices are very important. I noticed that. So there was this solicitation system, and I nominated myself to go to IC department, and liquid control 3D controller, and also capacitator, a method touch panel controller. In 2018, we released our 8K TVs and video engine Medalist Z1 was another project that I was able to engage. So I've done many multimedia things, but this time around I was told to take on the challenge of next type of challenge. So in relation to the AI, I've been thinking about a lot of things, as was mentioned by Dr. Ito, Edge AI and Cloud-side AI. Both of them have to be integrated with each other, but cloud and edge is connected by nerves or communications. So capacity has to be large for a vision and audio, but motor nerves have to be quick, and also many peripheral nerves have to be numerous, and they have to be connected to numerous points. So using this kind of a model beyond 5G communications can be very promising, because all of them, rather than all of them being realized simultaneously, depending on the purpose of what combination is the best, we should be able to select that, and I believe offering such a selection is a very important point. Please go to the next page. So what we are working on is this one. On the left-hand side, there are some visuals about beyond 5G software-defined radio platform. Put simply, beyond 5G is something that is going to happen in the future, and it'll be part of the technology, and you'll be able to touch it as part of the platform, and that platform is what we'd like to develop in our project. And there are some blocks down below: multi-core parallel computation DSP. There are 4 of them. By using software, modem is built, and then later on some measurements are written so that we can respond to all sorts of protocols. So we taped that out today. So Dr. mentioned that I will have a sleepless night tonight, because going forward I think I will have many sleepless nights. So if this works well, of course, users want to try using it, because there are many variations in the world of IoT, so they want to try this for various solutions. So with such customers, SoC software and partly hardware, but mainly software will be tuned up. And for example, local 5G cell mouse and hand mouse part will be perhaps reduced, and so on, so that power consumption can be reduced. This is one simple example, but in a spiral and agile manner, SoC, SoCA, B, C will be developed while they get separated. So this is more of a deduction approach. From the main SoC, we will carve some parts out, and then they will be developed separately. So first you will tweak the platform. Traditionally, manufacturer would be using the platform, and then software was prepared and offered. That was the main format of solutions. But in the times of IoT, there are more options. So there is a open platform. So with such open platform technology, we will let users use the platform, and in the end, there are more varieties of products which can be realized quickly. We are trying to build such a system, and that is how we are working on our R&D activities.
Thank you, Mr. Horikawa. So let me introduce the third panelist from SHOP. In July, Panel Semiconductor Laboratories was established. And from that laboratories, we have Mr. Makita. His background is process technologies. So he will introduce the activities of panel semicon laboratories and also the direction that SHARP should aim for in the future. So Mr. Makita, the floor is yours. Thank you. I am Makita. Let me introduce myself. I joined SHARP, and since then, constantly I have been involved in process development for displays. My specialty is TFT, thin film semiconductors. So polysilicon and oxide semiconductor, IGZO, transistor development, apply that to display, and eventually mass production. That's what I did. And I was seconded in June to panel semicon laboratories, which just started last month. So in these laboratories, which is newly established, I want to talk about the purpose and what we are aiming for. Next page, please. So panel semicon laboratories, the purpose of our institute. First of all, we have panel manufacturing technologies. We have assets. Utilizing them, we want to develop state-of-art displays and new sensors and combine that with semiconductor technologies. By doing so, we want to develop product and services, new product and services. So what we call one spiral strategy. As one SHARP, we have brand business operations. We're working with them to develop products, design, manufacture products, and we would like to commonize our effort so that we'll be able to reduce costs. Panel semicon laboratories have R&D pillars. We have 3 of them. On the left-hand side, you see next generation display technology development. We would like to bring a new product that touches people's hearts and the display that is noticeable naturally. So these are the ideas that we have in our development. In the AI era, to meet user needs, display is there to provide information. So it is going to be a device that connects people and AI. Now going to the second pillar, right in the middle, which is new device development. So apply our technologies to sensor devices, display panel manufacturing technology, for example, utilizing a plane, so 2D sensing, we will be able to collect, draw more information from plane sensor, 2D sensor. Utilizing this technology, we would like to develop odor sensor or smell sensor. So giving this smelling sensitivity, sensation to AI. There are nice smells and ugly odor. We have a wide range of smells that can be taught to AI. Coming November 11th, when we have Sharp Tech Day, this smell sensor will be displayed at AI Corner. And sensors that are utilized in the AI era includes sensors that are placed everywhere to collect all kinds of information from networks. So sensor price needs to be reduced. Panel manufacturing technology can be applied to sensors to achieve low-cost sensors as well. And on the far right, the third pillar is panel and LSI in other words, semiconductor technology, semiconductor manufacturing process, integration of these technologies, as we have been discussing. When it comes to glass interposers are often used for panel packaging. But wafer level packaging cost reduction is not sufficient. We would like to add new values to create something new. For example, we can use a certain area to integrate more functions in a unit of area. You see IGZO there in the middle. We have IGZO device technology. Utilizing that, we will be able to support IC, and flexible is the key word. In the area of display, flexible substrate, we have already created these technologies. Utilizing these technologies, we will be able to make flexible shape packaging. You can bend the package, so it's an innovative packaging, and innovative design will be enabled by the flexible packaging. So these are the three technology development areas that we are focusing on under one sharp strategy. Thank you.
Thank you very much. So from here on, I would like to start the discussions. So today, we have three speakers who gave presentations, and also there were some more presentations from sharp engineers. And based upon them, in today's AI world, applications are becoming more diverse. There is a flexibility and customization needs. And Dr. Jian said that a chiplet is a new implementation method to reduce the cost, and development time can be shortened. He mentioned these points. And from Furika, regarding software-defined proposal, flexibility can be realized and design time can be reduced. Mr. Horikawa mentioned that. So this chiplet technology, in terms of SoC for the communications you are thinking about, do you think that this concept will work well? And in the near future, would you be interested in trying this concept? Could you comment on this? You can remain seated, Mr. Horikawa. Thank you very much. So within one larger chip, as I mentioned earlier, there are many DSPs. And making a larger chip and considering scalability. So this is very difficult to say, but it's like one element, just like a Lego or block, you can combine them to achieve complicated processing. I believe that this is really the best approach. And of course, this is a communications you're talking about. There is RF part and different processes. All of them have to be integrated. So I believe a chiplet can realize a flexibility. Maybe my language doesn't sound well, but this is really end-to-end. Very good ones or poor ones can be supported all at once by this technology. So I have hopes like that.
Explain the chiplet technology is very useful for the future communication SoC. How do you think about the application of the communication LSI? That means how do you think about the chiplet is very useful for the future communication technologies?
Yes, I think so.
Sorry.
Thank you. Sorry. Yes, for the same reason, it can be flexible. You can put in this communication. you can also design one basic engine, and sometimes you can put 2 of them, 3 of them, integrate together to come up with a different product. Actually, we are working with several potential customers, try to improve the doing this high-speed communication. For the same reason, it has a performance issue and a flexibility issue. So the performance and cost. Yeah, thank you.
Okay. Thank you for your comment. 確かにその堀川さん言われたように、その
As Mr. Horikawa said, so we have analog and digital parts. In a digital part, you can add new features only there in a digital part. And for the analog part, you can continue to use the old technology. So in this world of chiplets, I think this is very important in terms of making our operation faster. Now, Professor Suganuma talked about new implementation technologies, where he also talked about the interface standardization. Take chiplet technologies. If we want to utilize chiplets, you need to have standardized interface. You have to have standardized protocols. And it looks like US is leading the efforts of standardization. It's very interesting because US has been closed for a long time. They're now trying to become more open by leading standardization. ICU activities, UCLE technologies, for example, there has been a rapid development of standardization there. Can you talk about it? Yes, they were very fast. They were very fast in establishing that organization. The whole world was surprised. But it's not just one group. There are several groups working all at the same time. And they are trying to connect these multiple groups as well. So we have to understand what is going on. And we also want to propose a new chiplet technology and packaging technology. We want to contribute to implementation technologies there. Standards can be good or bad. So we have to hit the right balance. We talked about the IP. Yes, please, Dr. Chang.
You brought a point I really couldn't help to speak up. I think this is the best, most important point you just brought up. It's today I kind of heard there are many standardization consortium involved. Actually, standardization has 2 parts in my mind. One is a protocol. You really like be able to speak the same language. But I think it's more important is the performance. Performance, for example, today if you try for the I/O to communicate between one chip to the other on the same PC board, because the PC board, like for the personal computer, is that big, and the standard you had to be able to have one chip on one corner of this PC board, be able to drive the chip on the other corner, and they are very far away. If you want to define a standard, I'm not talking about protocol. For example, it's very simply with delta V. If you are so ambitious, you want to define a standard, you'll be able to use universally in every case. Then your standard will be very conservative. You'll be able to drive such a large board, one corner to the other. However, if I want to make it confine my standard to a particular technology, for example, for the AI, for the IoT, I know I have the ambition, I only want to make it connect to a very small PC board. Then I can make my standard much more aggressive. You can imagine if you want to be aggressive, you want to make a standard goes to universal entire world, any product, then your standard will be very loose. Then you pay the price for being able to drive such a long distance. If I confine my own application to AIoT product, and with a particular technology we have in mind, as my ecosystem, based on this particular advanced package technology, I can define it's only be working in this environment, then my standard can be much tighter, and I can have much better performance, not wasting the delay and the power for such a. There are many consortium define the standard today, usually very aggressive. They want to define a standard can be used universally. I want to conquer the world, and actually, I don't think it's the best approach. If Sharp come out to do the IoT, you define a standard just in my own definition, just working on the product I'm going to do, based on the advanced package platform I develop, then we can do much better.
Okay, thank you for your comment. So I recognize that there are some opportunities in the future collaborating with all stakeholders. 少し自己紹介も長くなって
So they were rather prolonged self-introductions, so we'd like to have a final part of the discussion. Mr. Kanazashi, you've been talking about all sorts of major subsidies in the US, and Japan is partnering with the United States, including these packages. A new LSI industry is being developed, and METI is making efforts to descend in 5 years and 10 years' time. In the international industry, semiconductor industry positioning of Japan, what is your blueprint? What is your vision? What sort of position do you hope that Japan will enjoy in 5 years or 10 years' time in terms of semiconductor industry? Well, I believe that there were some keywords in your remarks, and everybody tends to talk about pre-processing because they like it. As was mentioned by Professor Suganuma in his presentation, the US is working on microelectronics packaging, not just for civilian consumer use, but also for military use. The US is trying to develop packages and doing packaging, and this is the US focus. And also for Japan's industry foundation, considering that, including automotives and communication devices and IoT, are the strong foundations for Japan. So for these industries, including packaging, in what way can we supply semiconductors, parts and production equipment included? What can we do? We have to build such industry foundations. So that is the very important point. First and foremost, what's been discussed in the US is that especially in the space of design, how can we democratize that space? And how can we reduce time in that space? Unless you try to find answers to these questions, needs will evolve and the supply never catches up. So for the society as a whole, there will be distortions and problems. So you like a pre-processing, or in terms of hardware, you do post-processing, and you tend to focus on IoT. But while working on these topics, finally design and user side also have to be bridged. So ecosystem has to be established in Japan, considering all these points. That's what I want to realize. Thank you. Thank you very much. So we don't have too much time remaining, so the remaining discussion will be dedicated to the Q&A session. So I would like to give a wrap-up comment for the discussion points. Now, Moore's law is reaching the final limits, and to achieve the very final step, it will take so much time and efforts, but it could be a very small, minor step. So in a different alternative approach, can we realize a big jump or leap? I believe such a potential can play a game-changer role, and there is a potential for growth in this space. So in this area as well, Sharp is doing a lot of R&D and research, so I'd like to focus our resources on this topic. Panelists, thank you very much for your participation today. From now on, I'd like to start the Q&A session. Well, thank you very much to all the speakers. So from now on, we'd like to open the floor for questions and answers. And let me explain the process. If you have a question, please raise your hand. And if you are appointed, please stand up and wait for the microphone. A staff member will bring one to you. And then please ask your question. Please ask questions about today's lectures, speeches, as well as the panel discussion. In the interest of time, we may not be able to address all the questions. Thank you for your understanding. So if you have a question, please raise your hand.
ではお願いいたします。
Please go ahead. That's the person in black. Thank you. I'm Mototaka from Bloomberg. So I'd like to ask Sharp's employees. Rapidus is going to develop and manufacture state-of-the-art semiconductors. Who are going to use those advanced semiconductors here in Japan? 1 nanometer, 2 nanometer? I don't know how they are stacked. Without these technologies, what products are not produced? What are some of the products that you would like to produce based on these advanced semiconductors? And Mr. Kanazashi, do you have any wish for Sharp, how those technologies should be utilized by Sharp? So who would like to volunteer to answer that question? Horikawa-san, would you like to? Currently, we're using 12 nanometer. So what about 2 nano? As of today, we're trying to, well, we discussed chiplets and modularization. So put that aside. When you have complex SoC, large-scale memory need to be embedded. Up until 40 nano, capacitor-type embedded DRAM was useful. But when we have further miniaturization, it will be SRAM-based or cache. Temporary memory is needed for enhancing performance and reduce power. So how can we embed more memory? How can we connect with high bandwidth with DSP? So these are two important questions. Ito-san, would you like to respond to that 2 nano question? First of all, we would like to develop personal AI on the edge. In a way, in the past, we developed calculator. So it's almost like AI calculator, achieving low power consumption. And on the other hand, as I said earlier, it needs to achieve a certain level of performance. These two seem to be contradicting with each other, but in order to achieve both, we have to have latest state-of-the-art semiconductors. So, see, I am on the user's side. So we have great expectation out of those new process technologies. So Mr. Kanazashi, representing METI, the Japanese government. So as Horikawa-san and Ito-san said, and I also touched on a few keywords in the earlier presentation. Basically, how AI is going to evolve. So we have one single model. Are we going to have dedicated models or specific models? And in the area of edge devices, we only had to achieve small power consumption, but we would see the AI accelerator developing. And I think one of the examples would be communication. When we have internal discussion, we talked about AI area and edge area. These two are two important categories. We also talked about design. How can we customize the device for specific applications? How can we reduce the cycle? And these are the demands that we have in Japan. We are going to start a design project. In such a project, we would like to try to achieve those targets, not just within Japan. In Europe, they are working on exactly the same topic. So we will be collaborating with European counterparts so that we can develop new businesses based on design. And to that question, I would like to also share my own personal observations. When it comes to 2 nano, design required for time required for design, the cost for the design are going to be substantial, as Dr. Chan said. You may want to narrow the functions. Well, you can utilize 100 applications, and you can actually select a core. You narrow down the applications, and you can apply chiplet technologies to that. Of course, with 2 nanometer, you have to achieve high volume, unless otherwise you would not be able to produce wafer. So how can we achieve customization based on narrow standards? Thank you. Are there other questions?
You can make a comment about how you saw the discussions and so on. Anyone? Yamanaka-san, please. Yamanaka of Keio University. Thank you very much for this opportunity today. So Dr. Jan used the example of Lego blocks. So it's a modular approach, and in a flexible way, all sorts of things can be mobilized. And for the LSI, this is a very important approach. And Ito-san talked about interactive AI, meaning that multiple AI are integrated with each other, creating next level of knowledge. I believe that this will happen in the future. It is like a collective knowledge of people. If this is the case, then chiplets don't have just a standalone function, but in a networking manner. This is more of a network function, as was mentioned by Horikawa-san. So my question would be that ion, optics, and electric integration by using optics or lights network function as a whole, rather than the substance of LSI, this is more of a focus, it seems. So optical technology is used to integrate chips and coordination amongst the chips. What is your idea about the potential of optics? Thank you very much for your question. Anyone? Dr. Ito, perhaps you can talk about, for example, optical technology is mobilized by NTT Docomo and so on. They are making new technology available and so on. So Professor Suganuma, please. Well, thank you. Thank you very much. I am not an expert of optics technology. I think you're talking about cold packaging. And Japan used to be very strong in this area. Unfortunately, outside of Japan, commercialization took place before Japan did so. And domestic development tends to be focusing around long-distance packaging communications technology. And this is a very important technology. For example, within data centers, communications taking place in them is important. But I think you're talking about more near-distance communications. And this is one good target. So this is about materials and connectors. We need to standardize them. So in Japan, we should take on this new challenge. We don't have enough human resources or talents. We have a depleted talent pool. We have scarce talents. So this is one area where I'd like to strengthen efforts. Thank you very much. From the Sharp side, any questions about your expectation on Eon and so on? Okay. Well, as was mentioned by Professor Suganuma, in this hybrid environment, how to utilize optics technology so that you can have an optical interface within chips. In terms of boosting performance, this is very promising. So you also have to change the protocols to a great deal. So in 5 years or 10 years' time, with such longer time horizons, there will be a generation change, and we have to monitor and observe that. But chiplet interface and other platforms and foundations, some kind of a connection using optics technology and so on, can be standardized going forward. Then Japan can enjoy its stronger position, leverage its stronger position. This morning, 3-5 compound background, that is his background, Dr. Jiang. And also I come from optics technology background, and one challenge here is that reliability has to be secured for optical devices. I believe that this is one challenge, so I have high hopes for this particular area. Thank you.
他に、質問
There are other questions. We are running short of our time, so next question will be the last question that we can take. Any other questions from the audience? If not, we would like to conclude our panel discussion. Thank you for listening. So we would like to ask Dr. Jiang, Professor Suganuma, and Mr. Kanazashi. Thank you very much. Please give them another round of warm applause. Thank you so much. You may now descend the stage.
どうぞ拍手でお見送りください。
Please once again give them a round of applause. As we informed at the outset, SHARP will hold the SHARP Day in November this year to commemorate the 111th anniversary of its founding. Please take a look at the screen.
SHARP Tech Day は11月10日から
SHARP Tech Day will be held at Tokyo Big Side, East Hall 8 from November 10th to 12th. During the 3 days, we will present a unique opportunity to introduce various original technologies. There is no need for pre-registration. Event is free to enter and exit, so please come by all means to our event. With this, we would like to conclude SHARP Tech Forum. As we said already, you are asked to answer the questions in a survey online. Please utilize 3D barcode and information card you received to access the survey site.